Hi, my name is Emanuel Istratoaie, and I will be presenting this video going through the research conducted by myself and Ionosphere on the use of artificial intelligence for the forecasting of the disturbance storm time index. In this video, we'll outline our motivation and describe the data analyzed. We'll summarize the implementation and optimization of the LSTM model, then compare it to similar architectures. Finally, we will discuss potential future improvements. Given that this presentation is focused on machine learning and artificial intelligence, I found it fitting that all the artwork presented should also be created by AI. So please sit back, enjoy the AI-generated art, and let's begin. Throughout history, the ability to predict the future has been desired by many, but attained by few. This ability has been valued because it allows the individual to minimize risk, improve decision-making, and gain a competitive advantage. Among all the important data that can be forecasted, such as temperature and stock prices, lays the Disturbance Storm Time Index, also known as the DST Index. The DST Index is a measurement of the solar activity as well as the Earth's magnetic field. When the solar winds transfer energy to the Earth's magnetic field, massive geomagnetic storms can be created. The DST measures the severity of these storms in nanoteslas at 4 geomagnetic observatories. This index is essential in analyzing the strength of these geomagnetic storms and is therefore valued in finance, energy, and communication sectors. In finance, an investor uses the index to trade stocks in industries reliant on space weather, like insurance and satellite companies. In energy, the index provides useful data in managing the power grid and avoiding blackouts. And in communications, the DST index warns of space weather events that could disrupt satellite and communication systems. Thus, a model that can accurately predict the DST index would be valuable to many facets of society. As such, we began to research a model that can accurately predict the DST index. We used a time series dataset of over 370,000 data points from the years 1975 through to 2018. The data was divided into 3 sets: training, validation, and testing, which included roughly 80%, 8%, and 12% of the data respectively. The training set was employed to teach the model important patterns and relationships. The validation set was used to evaluate the model's performance and fine-tune parameters. The testing set was used to assess the final performance of the model on unseen data and estimate its real-world performance. Once the statistics of the data were analyzed, we had found that the data had a mean of negative 15.5, a standard deviation of 22.9, a minimum value of negative 589, and a maximum value of 81. All of these values, of course, being in nanoteslas. This image focuses on the 30-day period depicting a superstorm. We can see that the DST index drops below, that when the DST index drops below negative 50, there's a moderate storm. When it drops below negative 100 to negative 250, there's an intense storm. And this can begin to affect satellites and when the DST index drops below negative 250, the superstorms that form can wreak havoc in space. Here is a graph that depicts the DST index for the period 1975 to 2018. It is a sample using every 100th data point. The mean is shown in the black horizontal line, and the single standard deviation from the mean in the red lines. Using statistical mathematics, we can assert that 68% of the data lay between these two red lines. Yet we can still see that there are many outliers that can create moderate storms or intense storms, or even this geomagnetic superstorm that was created in 2004. Now we can start to see the high variations in data, the many anomalies, and the lack of a strong seasonal trend, which would make using a conventional statistical model such as a regression model quite difficult. Therefore, an artificial neural network seemed to be the most appropriate method for forecasting this type of data. So armed with this information, we began to research an acceptable artificial neural network model, and the next section will discuss the architecture of the model that we chose. Convention dictated that there was a choice between a recurrent neural network or a long short-term memory network for time series forecasting. An RNN is a simple architecture that only captures temporal or short-term dependencies in the data and therefore cannot account for long-term trends. We chose an LSTM network based on the RNN architecture for its ability to combine short-term fluctuations and long-term trends to learn patterns in the data and forecast the Dst Index. The LSTM network inherits this ability since each memory cell in the network processes information via three parts called gates. The first is called the forget gate, which decides which previous cell information is irrelevant and therefore forgotten. The second is the input gate, which updates or adds new information from the current cell input. The last and third cell is the output gate, which passes the updated information from the previous two gates, and it makes a prediction which is passed to the next cell. This process repeats itself in the next cell as well. The internal principles of the LSTM network can get quite complicated as it involves sigmoid and tanh functions, as you can see here. Therefore, an accompanying resource will be provided that delves deeper into the model's architecture for those who are interested in the challenge. Meanwhile, we will move on to the implementation of the model. We used Keras, a well-known deep learning library in Python, to set up and train the model. The training process was accelerated by utilizing Google Colab, which offers free access to cloud-based GPUs. This is because artificial neural networks perform significantly better on GPUs as opposed to CPUs due to parallel computing. The initial model consisted of an input layer, a single recurrent LSTM layer, followed by two dense layers. To assess the model's performance, we chose the root mean squared error metric. This metric is commonly utilized in regression problems and represents the difference between the predicted and actual values. It does this by taking the root of the mean of the squared differences between the prediction and the actual values at a given point. Thus, by decreasing the RMSE, the accuracy of the model is also increased. Upon integrating the model into our code, we set out to improve it. We optimized the model through hyperparameter tuning. This involved manually adjusting parameters that are not learned during training, such as the batch size, the learning rate, and the number of epochs. We aim to improve the accuracy, complexity, and time cost of the model. The accuracy was measured using the RMSE value. The complexity of the algorithm was reliant on the number of parameters, and the time cost was the time taken to train the model. The batch size refers to the number of previous data points used in the prediction of the next data point. The learning rate refers to the speed at which the model updates its parameters. and impacts the weight of the network. The number of epochs relates to the number of passes through the dataset. After trials, the best accuracy for the single LSTM was obtained using a batch size of 8, a learning rate of 0.0001, and 10 epochs. This configuration resulted in a model that fit the data in 357 seconds with 17,425 parameters, resulting in a moderately complex model and an RMSE value of 4.66. This low RMSE value indicates that the model's predictions are, on average, very close to the actual values. We can see how the manual hyperparameter tuning was completed by changing one hyperparameter at a time until the highest accuracy and efficiency is achieved. We can see that the hyperparameters batch size, learning rate, and epochs are listed here, with the best iteration on the last line. We can see that the number of parameters remain the same throughout each iteration, and this is because the model structure was not changed. This will change and become more useful in the next section, where we'll discuss how the single LSTM network stacks up against the other models. We compared the single LSTM model to a double LSTM, a one-dimensional convolutional neural network, a 1D CNN, and a gated recurrent unit, or a GRU, with each model's architecture being vastly different from the others. The results show that compared to the single LSTM model, the double LSTM had a higher complexity, a higher time cost, and higher accuracy. The 1D CNN had lower complexity, lower time cost, and higher accuracy. The GRU had lower complexity, lower time cost, and lower accuracy. Interestingly enough, the 1D CNN performed marginally better than the single LSTM model, so that may be a model that could potentially be researched a bit more in the future. Despite this, the LSTM model was acceptable in terms of accuracy and complexity. Ultimately, different models may be more suitable for different applications, depending on which attribute is prioritized. The graph depicts the Dst Index predicted by each artificial neural network compared to the actual Dst Index that was recorded. It's depicting the first 100 time steps of the testing data, and it can be noted that all models performed quite similarly throughout the testing process. The predicted values are also very close to the actual values, signifying a high accuracy. By all accounts, it can be noted that the single LSTM model demonstrated the ability to generate reasonably accurate predictions. However, we still want to refine and further understand the algorithms. As such, there are a few improvements that could be considered. For example, alternative artificial neural networks such as the double LSTM and the 1D CNN could be optimized, as they may provide a more powerful model when tuned. Implementing a dynamic learning rate that adjusts based on the number of epochs may optimize the model's efficiency and accuracy. Additionally, a multivariate LSTM network could be implemented which considers time series of other space-related variables. These variables could include the total magnetic field vector B, the Z component of BZ, density of particles N, velocity v, and radio F10 flux, to name a few. And this would hopefully allow us to forecast more accurately. Finally, utilizing the model to predict multiple data points ahead could also be considered. This could be implemented using actual and predicted data points to forecast multiple data points ahead. For example, we could be using the 9 we could use the 9 most recent observations along with the next hour's prediction to estimate the Dst index 2 hours ahead. Ultimately, the search for a suitable forecasting model that can accurately predict the Dst index was fruitful. From analyzing the data and choosing the artificial neural network to implementing and optimizing the model, our research yielded acceptable results. We can conclude that the single LSTM model implemented using Keras and Google Colab had a good balance between accuracy and complexity. We compared the models to various other architectures such as the double LSTM, the 1D CNN, and the GRU, showcasing the trade-offs between accuracy, complexity, and time costs. And although the model performed well, there are still opportunities for improvement, such as fine-tuning the alternative artificial neural networks or predicting multiple data points ahead. Therefore, while the research was a success, further analysis and experimentation will be necessary to continue improving the accuracy and efficiency of Dst index forecasting. Thank you for listening.